All right, here's a quick Jacobson exercise. So, what do we know? We know that m equals 1, and then S1, the product of S1 through S1, S2, all the way up to SR, where each SI is contained in S. And we know this. This is some. If you don't know this, then read the textbook and you will know it. So, anyways, we know this, and we must prove that every element of M is, well, not is invertible, but has an inverse in M. So let M be an element of M. And write M as S1 through SR, where each of the SRs or each of the SIs is an element of S. Since each SI in S is invertible, then the element, let's call it M prime, which is going to be equal to SR inverse, product all the way down to S1 inverse. So it'd be SR inverse, SR minus 1 inverse, all the way down to S1 inverse. So it's M backwards. It's literally what you would get if you were to write M inverse, because what you'd have is you'd have come on, computer, M inverse equals this inverse, and then because of how inverses work, you'd flip the order and put the inverses on the inside. So, right. I'm actually impressed that I erased all of that without erasing what I had already written. So anyways, this element is in S. No, it's in each SI inverse is in S, and thus M prime is in M. See here. Then, and it's pretty clear that M prime here, I'll write it out, is S1 through SR inverse, all the way through S1 inverse, and this you just, like this here is 1, and then the next thing will be 1, and everything will cancel out and become 1, and so this whole thing will become 1. And that's all. You don't need to check the other direction, because if you have an inverse, like AB equals 1, then, so here, what do you do to prove that BA equals 1? It's like an easy thing. See here. You multiply on the left and right by AB equals 1. So AB equals 1, then AB squared equals 1. So AB equals 1, then AB squared is 1 squared, which is 1. This implies AB equals, oh wait, no, you have inverses. Oh wait, yeah, so AB equals, let's see, we have A inverse, because you multiply by inverse on the right, B inverse on the left, and this is BA. So this is all you have to check. I don't know why I did this because I'm pretty sure this is stuff that you've already covered at this point. But yeah, it's just verification that m prime equals this. And so m prime equals m inverse, which is in M. Hence, M is a group. And this completes the proof, because we had a monoid, and the only difference between a monoid and a group is that in a group, all the elements are invertible. And we know that all the elements are invertible, and so we have a group. And there we go, we're done.